Welcome to Ask and Learn.
So before doing the parts of the problem, let me remind you that for a complete rolling motion, we can write the velocity, which is the velocity of the center of mass, to be equal to the radius of the ball times the angular velocity. And this is only valid when the motion is completely uh, rolling motion. But in this problem, since the ball is initially slipping as well while it rolls, therefore this condition or this relation between v naught and omega naught for the initial motion of the ball is not valid. Therefore, we won't be applying this relation at all. So whenever we have to use the initial velocity, we will be using v naught, and whenever we have to use the initial angular velocity, we will be using omega naught without using this relation. Now, you must see that from the free body diagram, uh, so basically this diagram, the diagram of the ball, is after it has moved away from the initial point where O is the initial point. Now there are three forces acting on the ball, as you can see. The frictional force, in which I have drawn to be opposite to the direction of motion of the ball, direction of motion of the center of mass of the ball, to be specific. And there is a normal force from the ground at the point of contact of the ball and the ground, and there is weight acting from the center of the ball. Now, Fn and mg, as you can see, are in opposite directions, and each has the same lever arm about an axis passing through the point O, perpendicular to the plane of this paper. Now, because of that, there will be no torque, no net torque. This is because now if you calculate the torque about point O, so let me just do that. So net torque about point O will be equal to I alpha, or we can write that, let me use the other relation. So we know that net torque can be written as change in angular momentum over time. Now let's find the torques about this point O, which is the initial point of the ball. So since this frictional force passes through that point, so we have no torque due to this frictional force. Now if you take clockwise torques to be positive, then we have Fn giving a counterclockwise torque, therefore a negative sign, and the distance is r, and we have mg giving a clockwise torque and the distance is r as well. The distance r is the perpendicular distance of either force from O, and that is equal to dl over dt, which is the right side that we wrote. This means that Fn negative Fn, so let me just write the other way. So this gives r times mg minus Fn to be equal to dl over dt. Now if you write Newton's second law for equilibrium, you have, so there is no acceleration of the ball in the vertical direction. Therefore, we can say that the ball is in equilibrium in the vertical direction. It's moving, but it's moving to the right, so it's moving horizontally. But vertically, there is no acceleration. So we can write the net force in y direction to be equal to 0. So this gives Fn to be equal to mg, which are the two vertical forces. Now, if you apply this condition over here, you'll get that this term goes away, goes to 0. This means we can write dl over dt to be equal to 0. And therefore, L is a constant. Now we are done with the first part. So for the second part, we follow the hint, this hint, and we follow the hint given in the problem and express the total angular momentum as a sum of two terms, so which is angular momentum over, with respect to the center of mass plus angular momentum, the rotational angular momentum about W. So for the angular momentum for the center of mass will be mr times the velocity of the center of mass. So we have mass times the radius times the velocity of center of mass. And the angular momentum of this will be due to the rotational motion of omega. So that will be equal to I times omega. Now the angular momentum is a constant. So we equate the angular momentum at the initial position with V center of mass equal to V naught, and omega is omega naught, or we can also call it to be omega c. And final angular momentum is 0. Velocity of center of mass is 0 and omega is 0 as well. So if we do that, so let's write, since angular momentum is constant, so initial angular momentum is final angular momentum. Now we use this relation over here. So we have mr vcm plus I omega initially equal to mr vcm plus I omega for the final angular momentum. Now let's plug the values for the initial motion. So we have mr v naught plus I omega naught. And this is equal to, so finally we have this term, velocity of center of mass 0, and also omega is 0. This means that the right hand side will be 0. So from here we can express omega naught or omega c to be equal to mr v naught over I, and I forgot to write that this is the moment of inertia with the center of mass. So basically, if you are getting confused about how to arrive at this relation, remember the relative velocity addition. So let me just write that over here. So velocity, according to relative velocity addition, velocity of A with respect to O can be written as velocity of A with respect to B plus velocity of B with respect to O. Now, considering this is your point O and this is B, and let's say this is A. So we can write that velocity of, so we will apply this velocity, extend this velocity relation to the angular momentum. So we can write angular momentum of, I guess I marked the notations wrong. So let's call it A, let's call this point B and this point A. So let me just write the relation for this over here and just forget about this. This is true in fact, but the A and O here don't correspond to A and O here. So let me just write the relation. So we can write the velocity of B with sorry, you have to write for angular momentum. So we can write angular momentum of B with respect to A. We can write that to be equal to angular momentum of B with respect to O plus angular momentum of O with respect to A. And angular momentum of O with respect to A is the angular momentum of the center of mass. And angular momentum of B with respect to O is I times omega, where I is the center of mass of the ball. Yeah. So now we have, yeah, that's how we arrive at this relation. Now we have the initial angular velocity and I is the center of mass, moment of inertia of the center of mass. Now we know that the ball is spherical, so center of mass, inertia, moment of inertia of center of mass is 2 by 5 capital small m r square. Now plugging this expression to over here, you'll find omega c to be equal to 5 v naught over 2r. And this is the expression of omega c that we will be using in the further parts of the problem. So this is the answer. Now for part C, angular momentum is again conserved. So, but in this case, velocity of center of mass is v naught, but the initial velocity is 0.9 times omega c. And in the final state, the ball is purely rolling. Therefore, we have v center of mass equal to omega times r, and therefore omega is v of center of mass over r. So here, let me just write the condition for constant angular momentum. Now we will use this equation again over here. So initially we have mr, velocity of center of mass, plus I times omega naught, which is 0.9 omega c. Then for the final motion, we have mr, velocity of center of mass, plus I times omega, I times the final angular velocity, which can be expressed as velocity of center of mass over r. Now we can simplify this equation in order to get v naught. So first we can substitute the value of omega c that we calculated here over here, and also express I in terms of mass and radius. So basically use this relation and this relation over here and solve for the velocity of center of mass. So doing that, you will get the velocity of center of mass to be equal to 1 over 14 v naught. Now, this answer is pretty reasonable. There is not enough backspin since now omega naught is less than omega c. Therefore, the ball's final state is rolling forward. Now for the last part, again the angular momentum is conserved, so we write this relation, and for the initial motion we have velocity of center of mass to be equal to v naught, and omega naught is now greater by a factor of 1.1. Contradictory to the case in part C where omega naught is less than omega c. So that's for the initial motion, and for the final motion we have, again the ball is rolling, so we have omega to be equal to velocity of center of mass over r, the same relation that we used here. Now let's plug this equation over here, plug this equation, including this, over here, and you'll arrive at mrv naught plus I times 1.1 omega c equal to mrvcm plus I times omega, which can be written as vcm over r. Again, we can plug I to be equal to 2 by 5 mr square, and omega c, which we found in part B, this expression, we can plug these two expressions over here and find velocity of center of mass, which will come out to be equal to negative 1 over 14 times v naught. And this expression or this answer is also reasonable because there is more than enough backspin. Now that omega naught is greater than omega c, there is more than enough backspin. Therefore, this answer is reasonable, and so the ball's final state is rolling backwards.